Okay, so if you ever watched, basically any sci-fi movie with spaceships, or even something like Iron Man rocketing around,
Uh-huh.
you've seen that intense glowing heat during re-entry, right? That
Yeah.
fiery return trip.
Oh, yeah. Absolutely terrifying heat. We're talking unbelievable levels of energy converting into heat basically instantly.
And the only thing standing between, say, the astronauts in that inferno is this layer of material, the thermal protection system, or TPS.
Exactly. And it's surprisingly thin sometimes.
Right. And here's the wild part. It's designed to burn away. It's ablative.
Yeah, that's how it works. It sacrifices itself, carries the heat away as it decomposes.
But that's a heck of an engineering challenge. Too thin and, well, disaster. Too thick and you're carrying dead weight, which can also kill the mission.
It's a very fine line. You need incredibly accurate predictions of how fast that shield will degrade under all sorts of conditions. Speed, heat, pressure.
And for the carbon fiber materials NASA likes to use, getting that prediction right has been tough because, well, you couldn't really see inside while it was happening.
Exactly. It was a bit of a black box problem.
So today we're doing a deep dive into a really groundbreaking paper.
Mm-hmm.
It's from 2025, published in Advanced Materials, called Carbon Fiber Oxidation in 4D.
Mm-hmm.
We're going to unpack how the researchers, Benjamin Ringel and Francesco Panerai from the University of Illinois Urbana-Champaign, Joseph Ferguson from NASA Ames in Stanford, and a big team from NASA, Berkeley Lab, Swiss Light Source.
A really impressive collaboration.
How they basically developed X-ray vision to watch a heat shield burn in real time.
It's a massive step forward. These carbon fiber materials like Fiberform and NASA's Peka heat shield, they're fantastic because they handle heat through that sacrificial burning.
But it's not just heat doing the damage, is it?
No, the real enemy, chemically speaking, is oxygen. Oxidation, high temperatures plus oxygen just eats away at the carbon structure.
Okay, so the problem for engineers was that their models were based on limited data, like before and after shots.
Pretty much, yeah. They didn't capture the nuances, how it fails differently in different flight phases. To really nail the models, you need to see the microstructure while it's oxidizing.
Which sounds physically impossible, like watching something burn from the inside out.
It definitely sounded like science fiction, but, well, they pulled it off.
Let's get into the secret weapon then. 4D imaging. So 3D space plus time. How on earth did they manage that?
Okay, so they used something called time-resolved in situ X-ray microtomography. You can just call it ECT.
ECT, got it.
And this wasn't just wheeling in a standard X-ray machine. They had to build a custom reaction chamber, basically a tiny furnace, that could operate inside the X-ray beamline while the carbon sample was oxidizing.
So they put it right in situ in place at the Tomcat beamline at the Swiss Light Source.
Exactly. A tiny piece of heat shield material burning under controlled conditions inside this incredibly powerful X-ray setup.
Wow. Okay, so what kind of detail could they actually see with this setup?
This is where it gets really impressive. The resolution was submicron. We're talking 0.81 micrometers per voxel, which is like a 3D pixel. Tiny.
Okay, that's incredibly fine detail.
But here's the 4D part. They could capture a complete 3D scan every single second.
Every second.
Every second. That continuous stream of 3D images over time is what gives you the fourth dimension. You're literally watching the degradation happen frame by frame.
A submicron movie of the material failing, that really is unprecedented, isn't it?
Totally. And it showed them exactly how the fibers were changing.
What did they see?
Well, they could see the virgin fibers. They have the sort of irregular, wrinkly cross-section. They call it crenulated.
Crenulated. Okay.
As the oxidation kicks in, you see the fiber actually shrink. The surface gets pitted, kind of eaten away, and the hollow center, the lumen, starts opening up.
So you're seeing the material literally being consumed at the microscopic level.
Precisely. You see the whole process unfold, which is crucial.
And this direct observation, that's what helps fix the models or build new ones.
It's much more than just validation. It provides the benchmark data needed for totally new, more accurate predictive models. Current models often have to simplify things, assume average states.
Right.
This 4D data shows the true behavior, how the microstructure really evolves over time. It sheds light on the whole ablation process.
Okay, before we dive into the different ways it fails, you mentioned a key physics concept that determines how it fails, something about a competition.
Yes, the Thiel number. It's usually written with the Greek letter phi.
Field number. Okay.
Think of it like this. It's a ratio that tells you what's faster, the chemical reaction burning the carbon, or the oxygen physically diffusing, like soaking into the material.
So reaction speed versus oxygen penetration speed.
Exactly. If the reaction is way faster, the teal number is high. If diffusion is relatively faster, the number is low. That number basically dictates everything that happens next.
Got it. So let's use that. Ringel, Panerai, and the team found 3 distinct ways the carbon oxidized, 3 failure modes based on this teal number.
That's right. They experimentally confirmed these different regimes based on temperature and pressure, which control that teal number.
Let's start with regime 1. They called it the surface scorch. Sounds dramatic, like the typical re-entry fireball we see in movies.
That's a good way to think about it. This is your high temperature, high pressure situation. The teal number is really high, so $50 is much greater than 1.
Meaning the reaction is super fast.
Blazing fast. The oxygen gets consumed almost instantly right at the surface. It just doesn't have time to soak deep into the material.
So the damage is intense, but shallow, like taking a blowtorch to wood.
Perfect analogy. Very aggressive oxidation, but it's confined to a really narrow zone near the surface. In their tests, this damage zone stabilized at maybe around 485 micrometers deep.
So less than half a millimeter. The surface burns away quickly, but the inside stays okay.
Relatively speaking, yes. The bulk material deeper in remains largely untouched, even as the surface recedes.
Okay, now for the contrast. Regime 2, the deep rot. You called this the silent killer earlier. This sounds less dramatic, but maybe more insidious.
That's exactly it. This happens at lower temperatures, so the teal number is low, fillers much less than 1. Now, the chemical reaction is relatively slow compared to diffusion.
So the oxygen has plenty of time to seep deep inside the material.
All the way through. It penetrates the entire volume. What you get is this weak, almost uniform degradation across the whole sample.
So from the outside, it might not look too bad. The surface isn't burning away rapidly.
Right. The actual mass loss rate is way lower, like 20 times lower than the surface scorch case. Visually from the surface, you might not see much alarming damage.
But, and this is the twist, right? The researchers found this still leads to catastrophic failure. How?
This is the crucial finding. Because the oxidation is happening slowly everywhere, it tends to attack the weakest points within the structure first. The binder material. Think of it like the mortar between bricks. The carbon fibers are strong, but they're held together by this carbonized binder. This slow, deep oxidation weakens those connections preferentially.
Ah, okay.
And they saw this in their videos. Even with minimal surface loss, this internal weakening led to what they called an abrupt collapse of the fiber structure. The whole thing just crumbles from the inside out.
Whoa. Okay, wait. So a heat shield can seem perfectly fine, passing visual inspection maybe, but internally it's being weakened everywhere until, poof, it just fails structurally.
That's the danger. It's like termites or dry rot in wood. You don't see the damage until it's structurally compromised and potentially too late.
That completely changes how you think about safety, especially during lower heat parts of the flight profile. You can't just worry about the surface burning away.
Exactly. Designing against surface recession isn't enough. You have to account for this hidden volumetric weakening.
Okay, wow. And the third regime, regime 3, the compromise. The mixed one.
Right. This is the in-between case. The teal number is somewhere around 1 approx. Reaction speed and diffusion speed are more evenly matched. They're both significant factors.
So you get a bit of both problems, surface burning and deep damage.
Pretty much, yeah. The worst of both worlds, in a way. You still get strong oxidation near the surface, but it's not quite as confined as regime 1. Significant oxidation penetrates much deeper.
How deep are we talking?
In their tests, the degradation zone extended further, averaging around 1,128 micrometers deep, so over a millimeter.
Okay, and that deep damage, even if it gets progressively weaker as you go deeper, still compromises the structure.
Absolutely.
Right.
It weakens the material through a significant portion of its thickness. This makes it much more susceptible to mechanical failure during flight, like chunks breaking off. That's called spallation.
Millimeter scale chunks shearing off sounds not good.
Definitely not good. It's a major erosion risk.
So connecting this back, this incredibly detailed 4D data, isn't just confirming theories, it's giving engineers the actual numbers and visuals they need to build way better predictive models.
Precisely. They use the 4D data as input for NASA's own software called PUMA porous microstructure analysis.
Uma.
And with PUMA, they could calculate how key material properties change over time and space within these different regimes. Things like thermal conductivity, how well it transfers heat,
Uh-huh.
permeability, which is how easily gases can flow through it,
Right.
and tortuosity, which is kind of like the resistance to that flow, how winding the paths are.
Okay, so as the material oxidizes and gets more porous, it makes sense these properties would change. It probably gets less conductive, maybe lets gas through easier.
Generally, yes. More porosity means it behaves more like air, less like solid carbon.
Hmm.
But the way these properties change is regime dependent, and that's the key insight. In regime 1, the surface scorch, the properties change drastically, but only in that very thin layer near the surface. You get a steep gradient from bulk values to near air values almost instantly at the reaction front.
Like a sharp dividing line.
Exactly. But in regime 2, the deep rot, because the oxidation is happening everywhere slowly, the properties change gradually throughout the entire volume over time. The whole structure is sort of softening uniformly in terms of these properties.
I see. So any model that just averages or interpolates between a virgin state and a fully burned state is going to miss that crucial difference, especially the danger of the deep, uniform change in regime 2.
Completely. It misses the spatial distribution and the evolution of porosity deep within the material. That's critical for predicting structural integrity and overall performance.
So this 4D data from Ringel, Panerai, and the team acts as the ground truth, the benchmark.
Yes, it's the benchmark data needed to validate the next generation of these complex ablation and material response models. It lets engineers fine-tune everything.
Meaning they can design shields more effectively. Maybe use specific coatings or binder materials tailored to resist the type of attack expected in different flight phases.
That's the goal. Tailored protection, better design margins, knowing exactly how much safety factor you need without adding unnecessary weight. Every kilogram saved is huge in aerospace.
And this 4D technique, while huge for heat shields, it's not limited to just aerospace, right? The authors mentioned other applications.
Oh, yeah, absolutely. They point out the method is applicable to basically any situation involving porous materials where phases are changing over time. Think about electrodes in batteries or filters or materials used for carbon capture.
Anywhere you need to understand how a porous structure degrades or changes from the inside out.
Exactly. It's about getting that dynamic internal view of failure mechanisms.
Okay, this has been fascinating. Let's try and boil this down. If you're listening, what are the absolute key takeaways from this deep dive into the carbon fiber oxidation in 4D paper?
Right. I think there are three main things. First, seeing is believing. This time-resolved 4D X-ray microtomography is revolutionary. It lets scientists actually watch the microscopic failure happen in real time.
Yeah, that sub-micron movie view. Okay, what's second?
Second, it's regime-dependent. How the carbon fails isn't one-size-fits-all. It depends critically on the Thiel number, falling into these distinct regimes, the fast surface scorch, the slow deep rot, or the messy mix. High-temp failure looks totally different from low-temp failure.
Got it. Different conditions, different failure modes. And the third?
And third, the big one, the silent killer. That slow, seemingly minor oxidation happening deep inside at lower temperatures, the reaction-limited regime, can cause catastrophic structural collapse by weakening the binder. It's a hidden failure mode traditional models would miss.
That internal dry rot effect. Okay, so putting it all together, what's the bottom line?
The bottom line is that understanding these failure details allows us to build much better thermal protection. Stronger, lighter, more reliable shields for everything from Mars sample return missions to hypersonic flight right here on Earth. It moves us from educated guesses to truly predictive engineering.
Perfecting the shield, kilogram by kilogram.
You got it. And maybe one final thought to leave you with.
Okay.
If this kind of slow internal degradation can cause sudden failure in heat shields, what other critical systems out there might be weakening slowly from the inside? Think about infrastructure like bridges or maybe components in wind turbines, even advanced materials and batteries. Are they experiencing a regime 2 failure we just can't see yet? What kind of imaging do we need to find their hidden breaking points before it's too late?